The grand enterprise of 18th-century science was a project of measurement, an audacious attempt to take the full measure of the cosmos as revealed by the Newtonian synthesis. Within this sweeping intellectual movement, few quests captured the imagination or commanded such immense international resources as the determination of the solar parallax, the tiny angular shift of the Sun against the background of distant stars as viewed from different points on Earth. This single, elusive value held the key to the absolute scale of the solar system. It was the celestial yardstick, the fundamental constant needed to convert the elegant ratios of Kepler's laws into tangible distances, transforming a map of relative orbits into a true physical architecture of the heavens. While explorers like James Cook became the celebrated public faces of this quest, braving Parallax ceased to observe the 1769 transit of Venus from remote shores. The ultimate triumph belonged to a quieter form of genius. It was a victory won with pen and paper, far from the decks of ships, in the quiet halls of the St. Petersburg Academy of Sciences. In 1775, the mathematician and astronomer Anders Johan Lexell published his monumental analysis, a work titled Determination of the Parallax of the Sun. This paper represents a pivotal moment in the history of science, a point where the brute force of global data collection was tamed and refined by the supreme power of mathematical analysis. Lexell's contribution was the alchemical transmutation of scattered, flawed, and often contradictory observations into a single, coherent, and astonishingly accurate value. He provided the definitive chapter for one of the century's greatest scientific sagas, demonstrating that the path to cosmic truth lay through the crucible of rigorous computation. The intellectual landscape that Lexell surveyed was dominated by the legacy of Isaac Newton, whose laws of universal gravitation had provided a breathtakingly complete dynamic model of the solar system. Newton's framework, however, was a system of proportions. It could predict with remarkable precision that Jupiter was approximately 5 times farther from the Sun than Earth, but it was silent on the actual distance in miles or leagues. The scale was missing. The English astronomer Edmund Halley, a contemporary and champion of Newton, conceived of a brilliant solution in a 1716 paper. He proposed using the rare astronomical event of a transit of Venus, when the planet passes directly between Earth and the Sun, as a cosmic measuring tool. By precisely timing the duration of the transit from widely separated latitudes on Earth, observers could use simple principles of trigonometry to calculate the distance of Venus, and by extension, the Sun. The baseline for this cosmic triangulation would be the known distance between the observers on Earth. The apparent path of Venus across the solar disk would be slightly different for each observer, and this difference, a direct consequence of parallax, would yield the coveted solar parallax angle. From this angle, the Earth-Sun distance, the astronomical unit, could be calculated. Halley, knowing he would perish long before the next transits in 1761 and 1769, bequeathed this grand challenge to future generations. His method was elegant in theory but fraught with immense practical difficulty. The 1761 transit mobilized the first major international scientific collaboration, with expeditions dispatched across the globe. The results, however, were inconclusive and disappointing. The data was noisy, plagued by poor weather, difficulties in establishing precise longitude, a bizarre and wholly unexpected observational art. The international scientific community, undeterred, mounted an even more ambitious effort for the subsequent transit on June 3, 1769. This was science on an unprecedented scale, a geopolitical spectacle involving the British Royal Society, the French Académie Royale des Sciences, and the Russian Imperial Academy, among others. Expeditions were sent to the ends of the earth, to Tahiti in the newly discovered South Pacific, with Captain Cook and the astronomer Charles Green to the frigid shores of Hudson Bay in Canada, with William Wales de Vardo in the far north of Norway, with the Jesuit astronomer Maximilian Helland to sites across Siberia, Mexico, and India. Each observer was tasked with recording the 4 moments of contact: the instant Venus first touched the outer edge of the Sun, the instant it fully entered the solar disk, the point it began to exit, and the final moment it departed. The entire enterprise hinged on timings accurate to a single second. Yet, the universe proved far less cooperative than Halley's neat geometry suggested. The primary antagonist was a confounding phenomenon that came to be known as the black drop effect. As Venus neared the solar limb, a small, dark ligament appeared to form, connecting the planet to the edge of the Sun and smearing the moment of contact into an agonizingly uncertain interval. This optical distortion, now understood to be a complex interplay of atmospheric turbulence, telescopic diffraction, and the intense brightness gradient at the Sun's limb, made precise timing a fool's errand. Observers, separated by thousands of miles, recorded contact times that differed by as much as a minute. a catastrophic level of uncertainty. When the initial reports filtered back to Europe, they presented a bewildering cacophony of conflicting data. The raw results yielded values for the solar parallax that were all over the map, some even worse than pre-transit estimates. The grandest scientific project of the age seemed to teeter on the brink of failure, drowned in a sea of its own imprecise data. Into this state of analytical confusion stepped Anders Johan Lexell, a Swedish-born Finn. Lexell had been personally recruited by the great Leonhard Euler to the St. Petersburg Academy, the epicenter of mathematical physics in Europe. Lexell was a quintessential product of the Euler school, a master of celestial mechanics and analytical methods, whose mind was perfectly suited to finding order within apparent chaos. Where others saw a collection of failed experiments, Lexell saw a complex system of equations waiting to be solved. His 1775 paper was a work of pure synthesis, a masterful reanalysis of the global dataset from the 1769 transit. He began by gathering dozens of observations from every available source, meticulously evaluating the credibility and circumstances of each. He understood that a simple averaging of the results would be a naive and useless exercise. The errors were systematic, tied to the specific location, instrumentation, and even the psychology of each observer. Lexell's great innovation was to treat the problem holistically. He constructed a sophisticated mathematical model that accounted for all known variables simultaneously. For each of the nearly 80 observations he formulated an equation that related the observed contact time to a set of unknown parameters. These parameters included the orbital elements of Earth and Venus, the precise geographic coordinates of the observer, the diameters of the Sun and Venus, and, most critically, the solar parallax itself. His method was a precursor to what we now call the method of least squares. He would posit a trial value for the solar parallax and calculate the expected contact time for each observer. The discrepancy between this calculated time and the actual observed time produced a residual error. The goal was to find the one value for the solar parallax that would cause the sum of the squares of these residuals, across all observations, to shrink to a minimum. This was a computational task of staggering proportions for an era without mechanical calculators. It required Lexell to solve a large system of linear equations, painstakingly manipulating vast tables of logarithmic and trigonometric values. He incorporated corrections for factors his contemporaries often neglected, including atmospheric refraction and the subtle effects of the equation of time. He even attempted to model the influence of the black drop effect by treating the internal and external contacts with different weighting schemes, recognizing some were more reliable than others. This analytical rigor moved the problem from the realm of pure observation into the domain of statistical inference. Lexell was essence, filtering the signal of the true parallax from the overwhelming noise of observational. The publication of Lexell's findings sent a wave of relief and admiration through the astronomical community. After years of confusion and debate, here was the result grounded in unimpeachable mathematical logic. His calculated value for the solar parallax was 8 6/10 arcseconds. This figure was a stunning achievement. It was a significant improvement over the scattered results that had emerged immediately after 1769 and stands remarkably close to the modern space-age value of 8 794,000 arcseconds. From his parallax value, Lexell derived a figure for the astronomical unit of approximately 150 million kilometers, a number that brought the true scale of the solar system into sharp focus for the very first time. The reception of his work was overwhelmingly positive. Jérôme Lalande, the leading figure in French astronomy, quickly adopted Lexell's result in his influential textbooks and tables, effectively cementing it as the standard value for the rest of the century. The St. Petersburg Academy, under Euler's guidance, had provided the definitive answer that the expeditions of London and Paris had sought. Lexell's paper was a quiet triumph of the analytical tradition over the empirical. It underscored a profound truth about scientific progress. The collection of data, however heroic, is only the first step. The extraction of knowledge requires an equally heroic act of intellectual synthesis. Lexell's work was celebrated because it rescued a massive international investment from the brink of failure. He had taken the discordant notes played by observers around the world and arranged them into a harmonious chord, revealing a fundamental keynote of the solar system. There were, of course, lingering questions. The physical cause of the black drop effect remained a mystery for another century, an host in the machine that Lexell could only mitigate mathematically. His method, while powerful, could only work with the data it was given. Flaws in the original observations were an inescapable inheritance, yet his approach represented the absolute best that could be done with the available information, a testament to the power of a single brilliant mind to distill truth from a sea of uncertainty. The legacy of Lexell's 1775 paper extends far beyond its immediate result. It established a new and enduring paradigm for precision astronomy, the idea that a final, definitive result could be achieved through the careful statistical combination of many imperfect measurements became a foundational principle of experimental science. Lexell's methodology directly influenced the next generation of celestial mechanicians. Decades later, in the 1920s, the German astronomer Johann undertook his own famous analysis of the 1761 and 1769 transit data in his work, which further refined the value of the solar parallax and became the standard for much of the 19th century, followed Lexell's template directly, and used a more formally developed method of least squares, articulated by Legendre and Gauss. But the intellectual spirit of his investigation, the systematic combination of all available data, within a rigorous mathematical framework, was a direct inheritance from Lexell. This tradition of re-evaluating historical data with new analytical tools continues to this day, a powerful engine of discovery in fields from cosmology to climate science. Lexell's work also elevated his own standing as one of the era's foremost astronomers. His name is more popularly attached to comet D1770L1, often called Comet Lexell, for which he calculated a startling orbit, showing it had made a remarkably close approach to Earth and had previously been captured and later ejected from the Jovian system. His analysis of the comet's orbit and this parallax paper were two sides of the same coin, both showcasing an unparalleled mastery of gravitational mechanics and computational technique. The parallax paper solidified his reputation as a scholar who could solve the most challenging problems of his day. It served as proof that the true frontiers of knowledge were being explored in a mind as much as on the high. In conclusion, and as Johann Lexell's 1775 determination of the parallax of the Sun stands as a landmark of 18th century science, a testament to the transformative power of mathematical reason. It marked the moment when the problem of the solar system's scale moved from the observer's eyepiece to the mathematician's desk. The great transit expeditions of 1769 provided the raw material, a global dataset rich with potential but riddled with error. It was Lexell, the quiet analyst in St. Petersburg, who supplied the crucial intellectual machinery to process this raw material into a refined product of enduring scientific value. He rose above the chaos of the black drop effect and the uncertainties of longitude to impose a rational order upon the data. His work was a profound validation of the analytical methods championed by his mentor, Euler, and it set a new standard for rigor in the physical sciences. While we remember the adventurers who sailed to the far corners of the globe, Lexell's contribution reminds us that discovery is a dual process of exploration and interpretation. The observers wrote the scattered words and phrases, Lexell composed the definitive sentence that revealed the grand scale of our cosmic neighborhood. His paper is more than a historical calculation, it is a timeless illustration of how the abstract beauty of mathematics provides the ultimate key to unlocking the physical secrets of the universe.